So your string can be pumped. And what does that mean? That you can divide the string into 5 parts like this, concatenated, and this division, this string S, obeys 3 conditions. Now the essential one is the pumping condition, and that is you can take this substring, the V and the Y, and you can pump them. And what that means is you take a second copy of V, this substring, and insert it here, like after the first one. So now you'd have U VV X dot dot dot. Now the Y here, so the second and the fourth part, they both get pumped together. Okay. Now what I mean by that is, if you pump this, let's say once, so you got VV, well then you'd have to have YY, right? So if you have I, little I, like this, if you have I copies of the V here between the U and the X, you must have the same number of copies of Y between the X and the Z. Okay, so it'll be of this form. So U V to the I, X, Y to the I, Z. That pumped, pumped in the sense it's made longer. It's like pumping a tire that, well, okay. Pumping in this context just means it's made longer. You make the string longer. So this pumped version of the string now with VI and YI, so the second and the fourth substrings are pumped. Multiple copies and inserted and concatenated, and right, so you get this. Now the result, the pump string, must also belong to the language. Okay, that's effectively what the pumping theorem says. Now there are a few other conditions as well on this pump string. The V and the Y here, their length. Like if you concatenated V and Y, like here, the length of that concatenated substring would be positive. Can't be 0. Right? That's a condition. So that's the second condition. So Vy, if you concatenate them, so the second and the fourth substrings, if you concatenate them, find the length. That length will be positive, non-zero, positive. Right? Of course, not negative. It's a length, right? So greater than 0. And there's another condition. This one. Now this is sort of similar to what we were talking about before. So Vxy. So Vxy. So if you take this substring, so the middle of the sandwich, if you like. So you take second, third, and fourth substrings concatenated. That length has got to be less or equal to p. And P, remember, is your pumping length. So let me sort of condense, give you the essence of the pumping lemma. We've done 2 versions of it now. One for regular languages, and now this one for context-free languages. So the basic idea of a pumping lemma then is, if you have a particular language, and if it's a certain category of language, for example, a regular language, or a context-free language, or some other specific kind of language, well, let's say for those 2, then for that language there'll be a characteristic positive integer, p. It's called the pumping length. So that all strings in that language that whose length is at least or more equal to that pumping length, all those strings are pumpable. That's it, effectively. That's what the pumping lemma says. That you can pump them. Now, if a string does not belong to that language, then maybe you can't pump it. If it does belong to the language, you can pump it. Therefore, if a particular string cannot be pumped, then that string does not belong to that language. That's its use. That's why the pumping lemma is so useful. Because if you don't have pumping lemmas, sometimes it's really hard to judge whether certain strings belong to a certain language or not. It's not obvious. You can be fooled, and hence the need for pumping lemmas. Okay, alright, so you get these three conditions. So the pumped string belongs to the language, Vy, its size, its length, in other words, it's got to be positive, and the size of Vxy is got to be less or equal to the pumping length. Right? Now, what's this saying here, condition 2, a bit of a note here, that you can't have both V and Y. In other words, the second and fourth substrings, you cannot have both of them being the empty string. Okay, so you can't have just like UXZ. One of them at least has to be not the empty string. One of them has to be not empty. Right? So if you concatenate Vy, so the length of Vy will be obviously the length of V plus the length of Y, right? And you can't have both of them being the empty string, because then the length of Vy would be 0, and that's not allowed because this has to be greater than 0. Okay, so that's, and if this were 0, then the theorem becomes trivially true. And I ask you to show that for homework. Right? Convince yourself that it's just trivially true, but it's not proven in the text. Okay, now condition 3. That's this one. What's that saying? Well, if you concatenate the middle 3, or if you take this substring here, Vxy, its length has to be less or equal to the pumping length. Okay. Now, what's the point? Now, this third condition, now we had something similar before when talking about the pumping lemma for the regular languages. It was useful, this third condition. We had a similar condition for the earlier version of the pumping lemma. And it's the same here. It's just useful in certain proofs, or actually disproofs, using proofs by contradiction. Okay? So, it's a bit technical, but very useful for proving stuff. And well, I haven't gone into the details of these 3 examples to come, but I assume this will get used, because it certainly got used several times in our 5 examples of proving that certain candidate languages were not regular languages. We used the equivalent of this several times before. So we probably will use this in the 3 examples to come, but I haven't looked ahead to see the details. All right. Okay. Now the proof idea. So we'll do that. One and a half squares into the next session. So you've got a language, right? And you're told it's a context-free language. So you start with that. So A is a context-free language, and G, obviously it's the context-free grammar that generates it. So that's what you're starting with in your proof. Well, this is the proof idea, the overview, and we'll do the details in later sessions. Okay? Now, so what we're trying to prove, the proof of the pumping lemma is you're just trying to show that any string that belongs to this language, any string A, S belongs to A is a language, okay? Then for the strings that have a length that's at least as large as the pumping length, this P, all those strings that have a length at least as large as the pumping length, little p, they can be pumped, and still they belong to the language. Even once they're pumped, they still belong to the language. That's the pumping lemma. So that's sort of the guts of it, like I was trying to say earlier. And there's a bit more to it, because there's condition 2 and 3 as well. Okay. Alright, now now we get into the guts of the proof, not the details, but you know, the essential idea. And in the next session, I will give you pictures, and that will help you understand what's going on. Right? Right. So let S be a very long string belonging to your language. Now, you know, how you define very long, we'll do that later. Okay? But just assume for the moment, let's assume it's long enough for us to be able to do stuff. It'll become clear what very long means. Right? So just hold on this, but assume that our string now S here, which belongs to this language. Let's assume it's very long, okay? And you'll see why. Well, next session you'll see why that's needed. Okay, so we assume it's very long. Now it's a string and it belongs to this language A, and then therefore by definition it's derivable from the grammar G. Remember, this G here is the context-free grammar that generates this language. Okay, so I assume you're familiar with that concept now. You know, what do grammars do? Well, they generate strings, and all the strings that they can generate, well, let's say one grammar, a particular grammar, all the strings that one grammar can generate, that's the language generated by that grammar. Okay, so this grammar generates this language. This grammar derives every string S that belongs to this language. And how do you derive? You start with a start variable. Remember, a grammar just consists of a set of variables, a set of terminals, substitution rules, a set of substitution rules, big R, and so on. Okay? So I assume you've been studying me and you now have a pretty clear idea how to use a grammar. Okay? So this grammar generates that language. Okay. So little s, which is assumed to be very long, belongs to the language, and therefore this string can be derived from the grammar. Deriving means it's the process. You start with a start variable, and then you replace it by the right-hand side of a substitution rule, whose left-hand side matches the start variable. And then progressively, you have a look at the intermediate string that you get after each substitution, and you replace a variable in that string by the right-hand side of some other usually substitution rule. And you keep doing this step by step, and that's called deriving, until eventually you get a string that's totally of terminal symbols. Okay? And then the derivation stops, because then you've derived the string. You've found the string by a series of substitution rule applications. Okay? So this string is derived from G. Well, it's derivable. You can get it from deriving from G. Right? So because this string can be derived from G, it'll have a parse tree. That string will have a parse tree. Right? You'll start with a start variable, and then step by step, eventually you'll end up with the string, well, usually a whole bunch of strings, because quite often you'll have multiple substitution rules in your grammar, where you have several, more than one rule, substitution rule, where for the same variable on the left-hand side of the rule, you may have several different strings on the right-hand side. So you will be able to derive many different strings, consisting totally of terminal symbols. At the bottom, at the leaves of the tree. The leaves of the parse tree are strings, consisting totally of terminal symbols. Right. Okay. So this very long tree, this very long string, it'll have a parse tree, and it may be very tall because it's very wide. This is very long. and therefore, if it's very tall, there's a tall paths tree, then it'll have a long path. Remember what a path was in a tree? From the root node to the leaves, to a leaf at the bottom of the tree. Okay, so it'll have a long path, and I'll just go straight on to the next session.